The table on the left shows the results in a math test. By GDC, we got the results in this table on the right. Suppose these 5 data constitute the population. Then the mean of the population mu equals 38. This standard deviation of the population sigma equals 11.7. The variance of the population sigma squared equals 137. Suppose the 5 data above is a sample from a population. Then the mean of the sample x bar equals 38. As you know, we do the calculation about samples so that we can estimate the parameters of the population. This x bar is the mean of the samples. It's also the unbiased estimate of the population mean. The standard deviation of the sample is 11.7. We will use this symbol, lowercase of s sub n equals 11.7. Variance of the sample s sub n squared equals 137. We know x bar is the unbiased estimate of the population mean. It's s sub n, the unbiased estimate of the population standard deviation. Answer is no. S sub n is not a good estimation of the population standard deviation sigma. We will use Bessel's correction n-1 to make sure the variance estimate is unbiased, meaning it expected value equals the true population variance. In the calculator, this x sub x is the unbiased estimate of the population standard deviation. We will use the symbol s sub n-1 equals 13.0 and s sub n-1 squared equals 169 as the unbiased estimate of the population variance sigma squared. If the 5 data constitute the population, this s sub x means nothing. Only when the data is a sample from a population, then this s sub x is unbiased estimation of the population standard deviation sigma. Let's work on this practice. X bar equals 53. S sub x equals 10.3. Sigma sub x equals 8.7 from GDC. Then, if the data constitute the whole population, mu equals 53. It means nothing. Sigma equals 8.7. If this data represent a sample of a population, then x bar equals 53. This is s sub n minus 1 equals 10.3. Means unbiased estimate of the population standard deviation. S sub n equals 8.7 means the standard deviation of this sample. Let's talk about the unbiased estimate of population variance S sub n minus 1 squared. Standard deviation measures how the data points spread out from the mean. So S sub n squared equals sigma x I minus x bar squared over n. S sub n minus 1 squared equals sigma xi minus x bar squared over n minus 1. Therefore, we got this relationship between s sub n squared and s sub n minus 1 squared. We do square root both sides. We got this s sub n minus 1 equals square root n over n minus 1 times s sub n. Also, you need to remember another formula. S sub n minus 1 squared equals denominator both n minus 1. Numerator, first one, sigma of xi squared. This numerator, n times mu squared. This mu equals sigma of xi over n. I will show you how to prove this formula. We do know s sub n minus 1 squared equals sigma xi minus x bar squared over n minus 1. For xi minus x bar squared equals xi squared minus 2 times xi times x bar plus x bar squared. So we get sigma xi squared minus 2 times sigma of xi times x bar plus sigma x bar squared over n minus 1. Denominator still n minus 1. Look at the numerator. Sigma of xi squared. X bar is a constant number. So we get 2 times x bar times sigma of xi plus there are n x bar squared here. So we get n times x bar squared equals denominator still n minus 1. Sigma of xi squared. We do know x bar equals sigma of xi over n. So we get sigma of xi equals n times x bar. This is n times x bar. So we got negative 2n x bar squared plus n x bar squared. Simplify. Separate. Sigma of xi squared over n minus 1. Combine like terms. We got minus this numerator n times x bar squared equals denominator is n minus 1. So we get denominator n minus 1, numerator sigma xi squared, this numerator n times mu squared. Because x bar is the unbiased estimate of the population mean mu. We know this mu equals sigma of xi over n.